That's right. Yes, 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 yes. You can. Okay. So can I hold on to my handset and speak? Is that okay? Just a minute. Just a minute. Just a minute. Okay. I'm just switching on from my handset to the speaker of my computer. Just see whether it is clear on audio. Hello. Hello. No, I'm not able to hear you back. I'm not able to hear you back over the. Okay. 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 So I'll keep my phone also handy so that if I have to speak to Priya, then I can speak to you on this. Okay. Mm-hmm. Okay. Just a minute. Just a minute. Just a minute. You can write in the where is the chat box here? Audio webcam questions. Okay, chat. Yeah, I'm just trying to open that one. Just a minute. Yeah. There you go. Yeah, can you see me now? Yes. Yeah, yeah, I'm here. I'm here. Okay, 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 okay. Yeah, go ahead, go ahead. Mhm. Sure, 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 sure. Thank you. Uh, I can see 36 out of 101, 37. Okay. Yeah. Sure. Sure, sure. Yeah. Yeah. Yeah, hi everyone. A few more minutes to join in. Waiting for others to join. Thank you. Yeah, hi everyone. My name is Tenan here. So I think we have enough participants joining in. So we would begin the session here. And a quick introduction on myself. My name is Tenan, and I come with 19 years of telecommunication experience working with a couple of organizations like Nokia, Qualcomm, Motorola around the globe. And today I'm going to be walking you through the mobile communication introduction to 5G. And there's a little chat box where you can type in your queries. Feel free to type in any queries which comes in. I would try answering most of the queries, and if time permits, else I would try sending it across over the mail. And for any technical difficulty, please stop me in through the chat. And I've already shared my screen, and I hope it is visible and my audio is as well visible. You can hear me well. So this is the content of today, what I'm going to be walking you through. And before getting into the content of 5G, this session is going to be for 2 hours. The last 10 minutes is for Q&A. Please feel free to raise any queries which you would have. And before getting into the content, the flow of this presentation, just to, to start with the transformation, what Telecom has been seeing from the first generation all the way to 4G. It was basically to do with the transformation of telecommunication only. But when we go into a 5G kind of a scenario, it is more to do with not only with the telecommunication transformation, but it's much more than that. It's a kind of an ecosystem which is going to be created, is what the world is going to be seeing. And it's a good news for all of us that there are a lot of opportunities which is going to be coming in, and that's going to be open up a lot of new business enterprises, and it's also going to enhance the service kind of an industry to a much larger. So it's an whole together. It's an ecosystem which is going to be built rather than just this shift of telecommunication what we've been seeing from 1G all the way to 4G. To keep the flow, I would yeah, to keep the flow, I would start off with the introduction to the 5G, how the IT revolution did takes place. To take you a little historic way back to 14th century, that's where the whole thing began. And then we have the 17th century where you have the industrial revolution, which we would see. Then comes the mobile communication transformation. Then the technological transformation. There are a lot of technologies evolved in the latest few years. So how is that going to be facilitating 5G? The 5G service features as compared to 4G is at a nutshell we would see that. And then the fifth generation telecommunication contributors, we do have a lot of organizations like Ericsson, Nokia, and what are the main contributions here? Why 5G? What brings in 5G? And I have a little video. If time permits, I would walk you through how Watch Your Day in 2020, which shows in how things are going to be changing. Then comes the revenue stream. I'm going to be speaking on what are the new revenue streams, where does India as a country stand from a GDP point of view, how things are going to be changing after 5G rolling in. I still have another video which shows of life simplified with connected devices, if time permits, or else I can send you the link where you can watch post the session. A little more technicality into it. 5G architecture. I will give you a a high level architecture on 5G. The power, the energy consumption. So the latest technologies what we've seen is from a shift from spectrum efficiency and bandwidth efficiency to energy consumption, because we have a couple of devices which is going to get connected. To be very frank, 52 trillions of devices on an IoT is going to get integrated under the narrowband IoT. So that's a lot of energy, consumption and work is dedicated towards energy consumption under 5G. The LTE architecture, we're going to have a comparison how LTE is moving towards 5G. The G Node B, the BTS, the new generation E Node B, the AMF and the UPF overview. The 5G service based architecture is another entity which I would like to speak on. Then coming into two aspects of 5G which are very important: the new radio, the NR radio, and the frame structure. We see how does it differ from a 4G kind of a scenario, and what are the the entities which gets added into the frame structure in 5G. To make this more interactive, I put in a lot of use cases to make you more, appreciating 5G. So it is IoT-based use cases under 5G, basically to do with the narrowband IoT. NB IoT is what I have some use cases here. The CNN-based use cases, this is a content-centric network kind of an architecture. If you talk of an entity like an Ericsson, they speak of user data consolidation. I have some use cases where it so speaks of retrieving lost objects in a smart city kind of an environment using a CCN. I've simplified again the use case. It's too early to speak of optimization in this small window of time, but then still I have incorporated a small use case where battery life optimization using some timers. People might recognize this timer T3314 in working on this in previous technologies as well. We have the 3GPP 22.862 is the latest releases of which talks of your ultra reliable low latency mission critical services, which was released just last 2 months ago. So I have few slides on that to talk. There are a couple of use cases which I have incorporated into how an industrial factory automation going to a bigger entity like a plant automation we would see. The television evolution, which is going to take place all the way to 8K ultra high density to 16K ultra high density, where 5G is going to be an enabler for this. Unmanned aerial vehicle, which is called drone. I have a couple of beautiful use cases, which I hope you would appreciate this. Virtual reality and position accuracy, also we have some use cases. If time permits, I would also walk you through the wireless propagation channel modeling using big data algorithm, because it is all data science encapsulated along with 5G, as we would see in the coming slides. So I welcome you all again once more. So introduction to 5G. The information technology really did not happen with the invention of microchip. It was much before that, 1400 or the 14th century, with the printing press by the great innovator Johannes Gutenberg. So this was the breakthrough, the first innovation which came through to accelerate the information technology. If really comparing a 300 page of a book, which is today, it would have cost $10,000 of those days when printing press was still not innovated. So it's a shift of an industry from a $10,000 to a $70, making information available to masses. Initially, the books were luxury items of nobility, produced one copy at a time, and it was all produced on a demand basis. So now information was shared for many people at a very low price, $70, a shift from a $10,000. So this is the first innovative information technology revolution which did happen in the 14th century. Now, then we see the Industrial Revolution. The Industrial Revolution is divided into four major aspects. The first one, which it did start way back in during the Second World War, is the new source of power, which was more to do with railway roads, coal, steel, and chemical industry. Then came, which was called as the mass production. So at the mass production, there were goods and services produced much before there was a demand of these items, and this made available for usage for the mass. Then came automation. There was innovation in elevators or lift, which you say. This gave rise to vertical growth of buildings. automobile industry, aircraft. This was a third shift of industrial revolution. And the fourth one is what we are witnessing today, the digital transformation, what we're seeing all together, which has a whole lot of, technology which is getting integrated into. The computers today, computers are made available even for a 30 to $40, like say Raspberry Pi kind of a computing device are available at a very throwaway price. IP addressing, we did start off with an IP4, now moving towards IPv6 and more towards content-centric network kind of an evolution. Mobile communication, as we all know, it did start off with 1G, 2G, 2.5, 2.7, 3G, HSDP, HSUPA, LTE, LTE Pro, and then now towards 5G. Under the cloud computing, there's a lot of innovations happen. We have storage as a service, instances as a service. Under the analytics, we do have big data analytics, big data, artificial intelligence, deep learning, blockchain. So when I talk about blockchain, let me put a use case, how things are going to be really affecting telecom. We have been experiencing international roaming, which is a costly affair. When we move into a country and experience that, always we are connected back to our home location register. This is not the scenario which we would see when blockchain comes in along with integrated with 5G. So the blockchain does the authentication, at the local, and so the user is benefited by paying the local currency rather than, a big ticket given to him due to international roaming. That's a kind of technological evolution blockchain is going to get in. Then we do have fintech. BrainNet is one of the latest technology which we would come into. So there's a lot of innovations which has happened recently, whether it is from a social media like Twitter, Facebook, YouTube, cloud computing, IPv6, companies like NVIDIA, where GPUs were a big success for processing, artificial intelligence, neural networks, then sensors, and a hell lot of entities which got innovated. If you really see from the last couple of years, to be very precise, 3 to 4 years, the amount of data that has been seen growing is huge. If you just see the statistics for a little window towards the rightmost corner, in 1 second, it is 2.9 millions of mails getting delivered, 72.9 product ordered under the Amazon. 1 minute, way back in 2013, it was 20 hours of data getting uploaded onto YouTube. Just by 2016, it rose to 150 hours of video. That's a huge amount of data growth which is happening. In one day, 375 Mbps of household usage, 24 petabytes of data is what Google processes, 50 millions of tweet, 1.8 exabytes of mobile internet data, 2017 is what witnessed. In 1 month, 700 millions of minutes of Facebook. That's a huge amount of data, and every year to year, the data is being seen 3 to 4 times the growth what it's been in the previous years. And how did the technology support? Cloud computing, we have storage as a service where cloud can store 4,000 exabytes of data and more. Data analytics, the intuition-based kind of a businesses, which is moving towards a statistical kind of a business where business can reap more profitability, more accurately, and they can also attain their break-even much faster comparatively. IoT, we have $11.1 trillion of business, connecting 52 trillions of devices across. Embedded system, as we did discuss, Arduino, Raspberry, Dragon Board, these kind of processing kits are available for $40 to $50 today, 3,000 rupees in mobile switching from a circuit switching to a packet switching. Sensors, we have a lot of sensors, which is into the kitty, acoustics, sound, pressure, proximity, along with the actuators, with this air, liquid, and water. The transformation from an IP has also gained a lot of momentum. It is from an IPv4 to an IPv6. So if you see the amount of data, what we did see now, 80% of the data which is accumulated or growing in the last few years are more to do with pictorial data, images, pixel kind of a data. So that's the reason why I have incorporated another slide, which is pretty interesting. I would take you to a little history. It's where the vision history starts. So taking you to 500 million years ago, this was where the world had species which did not have sensory organs. It was just the mouth, where the species could feed in when things comes very close to it, else it would stay hunger. So with the Big Bang theory, which it said that something which really did strike the earth. So what happened is there was transformation in this species. there were another organ started reforming. So just close to the mouth, there was another vacuum which was created, which is called as the first eye, the vision. So this was, able to attract or identify the presence and absence of light. This was the first eye which was built in the species. Then came, when the eye was developed, then we had all the other sensory organs coming in. Then we had the prey and the predator kind of a scenario going in. But fortunately, unfortunately, it was a two-dimensional eye which was created to compensate that what is where we have the two set of eyes to see the 3D kind of a world around us. So from 500 million years ago, now coming back to 2012, 2012 is a break even which we really had where algorithms, convolution neural networks, CNN, really made breakthrough to reduce the errors of image processing. This is where in the year 2012 machines can really, run in algorithm CNN and reduce the errors and really beat human, processing power. So since then, if you've really seen handsets where images were made available is post 2012. In fact, image recognition to be more precise. And since then, this has been going on, to more, much and more improvement. So 80% of the data is where I'm talking of here of the pictorial data. Now, along with 5G, 5G has evolved a long way with a lot of innovations which has happened in a different field. So things which came to my mind is what I have jotted down here. To start with, let me start off from the leftmost corner, the light blue. This is the television technology which is growing from SD to a fully high definition, 4K, pushing the technology to an 8K, ultra high definition, and ultimately to a 16K. I have a separate slide where we're going to be seeing what difference does it make from a 4K to a 16K leap. But then what is the user getting benefited is you're going to be having big screens which can support the quality of pixels under the 5G window, which is basically the enhanced mobile broadband kind of a scenario under the 5G. Then you have GPU, the processing power to 80%. As you've seen, it is image or the pixel data. We did not have processing power, so now it is GPUs which are powerful to to break down these images and give results. Then you have embedded system, which we did speak of, blockchain we did speak of, cloud computing. You have storage as a service, and then we have instances as a service. And from the reality, we have extended reality, mixed reality, virtual reality, and augmented reality. There are beautiful use cases which I have incorporated into this to make you better visualize how things are going to happen. And from a multi-layer or a cell densification, that's again a bigger pillar under the 5G, where this is going to be promising dense coverage or coverage which is not possible with the previous technologies, deep in penetration. BrainNet we did speak of. The narrowband IoT, 52 trillions of devices getting connected. That's a huge amount of connectivity which is going to be held by under the 5G. So it is not a man-to-man kind of a connectivity. It is going to be a mission-to-mission, man-to-man, and man-to-machine. Under the data analytics, we have deep learning, artificial intelligence, artificial general intelligence. If you really break down the artificial intelligence, again we have three platforms. The computer vision, which we did see the 80% of the images, which was a pixel based. Other the 20% is where it is dealt by the NLP, natural language processing, and then you have speech processing. So speech processing or signal processing, in fact, signal processing is the entity which really works with narrowband IoT. Then we have convex AI, reinforcement learning, and so on. From an IP point of view, we did shift from an IPv4 to an IPv6, making huge amount of IP made available. The next step or leap is towards a CCN, which is a content-centric network. We are going to be seeing more onto this. And from an antenna theory, we have beam forming, beam steering. I can really steer the beam with an angle theta, focusing a customer of his movements. Then massive MIMO, we have 64 cross 64 to 56 and going up to 1024 kind of a scenario. Therefore, web, we did start off with a web 0 way back in late 90s. And the progress is towards web 4. And we are now in between web 2 and 3 using HTML, XML, and moving towards RDF. So this is a semantic kind of a web where RDF, it stands for resource descriptive framework, where it is more to do with not only to connect systems but also to connect people. Now comes the mobile telecom transformation, which we have seen. People who have been working since 1980s would experience the brick mobile, which was the first introduced way back in 1980s. So there's a lot of transformation which did happen towards towards 4G, and now heading towards 5G. So what did what are these criteria which really push these technologies? When you see from a little the rightmost window, you can see here the 1G to a push towards a 2G was a voice quality, voice capacity. In fact, it's an analog to digital for a better quality. 2G to 3G was a high voice quality, and it was an introduction to a high-speed data. That's where we got introduced to. Then 3G to a 4G is a high-speed data services with a high bandwidth. The 4G, it's again to do with a ultra low latency and a high bandwidth. This does not stop here, and it is much more than that what we're going to be seeing here today. So, in a nutshell, what it says is the 5G is going to get a transformation from a www World Wide Web to a wireless World Wide Web. It is a www kind of a scenario, which is the transformation which 5G is really going to be getting into. Now, 5G also takes care of a few things. One is a vendor agnostic. Vendor agnostic, say if I have an Ericsson BTS, I can plug in Nokia radios into it. That's where the flexibility the 5G promises into. Protocol agnostic, it's open source. If I'm using a medical devices, I can hook into any of the systems. Then I have what is called as automation, with so much of data analytics coming in, self-optimized networks become possible enough. And cost is one of the most other scenarios which is talked about in the 5G, and the energy efficiency. Since we have so much of devices which is getting connected, energy efficiency is a big talk of 5G. From a cost-effective deployment, we would see slides where the deployment in 5G is much lower in a capex and opex for an operator point of view. So this is where the whole, in a nutshell, where we see from a telecommunication transformation from a 1G, 2G, 2.5, 2.7, 3G, 3G HSPA, HSPA plus, 4G LTE, LTE Pro, and pushing towards 5G to achieve a data rate of 10 MB, 10 gig, and even to 20 gig. The latency, what we've seen here. So similarly, there's another slide which talks of the same, the latency, which was way back in technologies like 1G and 2G of 110 plus. Now we would be able to reduce it to 1 milliseconds. So that's a huge amount of innovation which has gone into, and this is going to be opening up a lot of opportunities into different arenas. So, for example, the data rate, which is going to open opportunities into enhanced mobile broadband. Under the latency, we have ultra reliable low latency kind of a communication, and under the data rate, again we have a mobile massive mobile type communication. So what is this going to have is we can connect IoT devices here. So this is the this is in a nutshell how it gives you. So okay. So enhanced mobile broadband, EMBB, which promises of 10 Gbps and going towards a 20 Gbps, it gives services like a high definition TV pushing towards 8K and furthermore to 16K. Enhanced fixed wireline access. This is where we would be able to see wireline kind of an experience with a wireless kind of technology, 5G, where broadband at a residence becomes easy. The last mile optical connection, which would be difficult, I can connect it through my 5G kind of a scenario. Ultra low latency, less than 1 millisecond, unmanned vehicle, e-health, augmented reality, and so on. Mission to mission kind of a connectivity, which is an IoT, smart cities, smart homes, and so on. So this is where we are going to be comparing 5G services with respect to that of 4G. So to start with, let me start from the topmost corner. So peak data rate. So 4G promises for a peak data rate of 1 Gbps, now pushing towards a 20 Gbps. So as we have seen in an enhanced mobile broadband kind of a scenario, where the wireless talks of 10 GB with a latency of 1 millisecond. That's where we are able to achieve. So that's a arena of giving a last mile kind of a connectivity, where wireline was costly enough. This can be made effective with 5G with a very low cost of implementation. Then coming from a user experience, it is 10 Mbps to 100 Mbps is where the 5G promises. And this is going to be opening up a lot of new services which we are going to be seeing in today's session as well. Spectrum efficiency, it is 3 times the spectrum efficiency compared to an LTE. We have massive MIMO, which is a big accelerator to do this one. Mobility, 350 kilometers per hour movement is now transformed into a 500 kilometers per hour, giving rise to services like bullet train. Latency, we do push to 1 millisecond, where mission critical services, unmanned vehicle, all these kind of services blossom. Connected devices, we are expecting 10,000 devices per meter square. That's a huge amount of devices which is going to get connected under the IoT and the mission to mission kind of a communication in 5G. Network energy efficiency, it is 100 times compared to the 4G. Edge computing becomes more attractive into this. The area traffic capacity, this is 10 times what we find, and we have cell densification, where we are going to be giving deep indoor kind of coverage, which becomes possible with 5G kind of a scenario. So these are the pillars for the 3 kind of main services: enhanced mobile broadband, ultra reliable low latency, and massive mobile type of communication. Coming on to the next slide, these are some of the firms who are working towards, or organizations who are working towards achieving 5G. So if you see MOST, China uses a project called National 863, European Union 2020, METIS, UK, China, ITUR, Japan 2020 Brigade, Korea 5G Forum. And from the OEMs like Huawei believes to enhance more of capacity into the system. ZTE massive MIMO. Recently, we did have a testing, way back in Singapore for a MIMO of a 64 cross 64. Ericsson promises for a high data rate. So I have separate slides how Ericsson is going to be doing this with their innovations from a front haul kind of an experience. Nokia network expansion. So altogether, what is this aim from all these firms are high data rate, energy efficiency, spectrum efficiency, frequency efficiency, and ultimately ultra low latency. So why 5G and what brings in 5G, and that also why now? So see, as you have seen that the kind of data growth, what we have seen, especially whether it is with the pictorial kind of an data, or with the signals. So the content, or with social medias like Facebook, Twitter, YouTube, the content is made available. And even with the coming future of 5G with an IoT, we have more devices which is going to be good enough to collect a lot of sensor data. So the content is one thing which is a major driver. The second one is a computing. So much of data, were we efficient enough to compute in these previous years? No, it is recently that GPUs are made stronger to compute this big amount of data, huge amount of data analytics, which comes in as a major play, and connectivity, obviously. So we are able to get better connect, better bandwidth in a 5G scenario. So the kind of enhancement, it is 100 times the peak data rate is what we'll be seeing from the previous generation, 1,000 times the network capacity, 10 times the energy efficiency, and 30 times lower latency than before. So 5G does not aim only to connect smartphones. We can connect industries, robots, vehicles, homes, cities, enterprises, and you name it. You name the thing that can be connected. That's the power of 5G. And where are we now? So release 15 is what was talked in the early 2018, and release 16 is where we are also going to be seeing some of the slides which got released in July 2018. So it is the 5G new radio concept. We have two kind of an architecture which is called as the standalone and a non-standalone. Standalones deals more with the standalone 5G kind of a scenario, and a non-standalone is where pushing LTE towards 5G. So commercially, 2019 is what the phase 1 commercial is expected, and by 2021 is where the commercial launch for phase 2 is. Phase 1 deals more to do with enhanced mobile broadband, where it is more to do with wireline kind of a connectivity, which we did see, and more enhancement towards 5G is where we're going to be seeing in release 17 and going forward. How are we going to be testing these networks? We have Summer Olympics, Winter Olympics, FIFA, Expo 2020, Dubai Expo 2020. These are the scenarios where these networks will be getting tested for their efficiency. So this is a little video. I would not take time to play this. I can send you the link. People who are interested, post this, can watch this. So from a revenue stream point of view, from a 5G, so it's a new kind of a revenue stream. So fixed cost is for the past and pay per use is for the future. That's the value creation which 5G gets in. So from a mobile broadband, enhanced mobile kind of a mobile broadband kind of a communication, it is from an enterprise sector, it is going to be a white box kind of an approach. Say today, where we facilitate an ILL, a PRA kind of an approach, this is going to be a white box where this can be installed with a very less cost and quickly configurable. Virtual reality, augmented reality, there are a lot of beautiful cases which we're going to be seeing here. This is again a huge amount of revenue model coming in from there. Remote surgeries, field team can be better coordinated. High data rate, intelligent communication in internet of things, connecting everything, whether it is in industrial IoT, narrowband IoT, cellular IoT, or internet of everything. Ultra low latency, mission critical services, unmanned vehicle kind of services are going to grow for future, accommodating huge revenue. New service incorporations, new enterprises would emerge with new services which the world has never ever seen before. Zettabytes of traffic is what the operators would gain, but operators are not really going to be gaining from plain traffic, but is from the service kind of a thing. It's going to be a service kind of industry which 5G focuses more on. Automation, cost effective. Predictive analytics, we have big data, thick data, artificial intelligence, blockchain, we did see, and we have a system breakdown now and future. This is one of the case study which I've just put in here. So if it is before the 5G kind of a say present today, if a system breaks down, I would have to call an engineer or a technician and then get fixed. But when 5G comes in, so it is going to be predictive kind of a thing. So before the machine breaks down, I would see the percentage of errors what it would throw and say that, hey, from 100% of efficiency it's dripping down, and I can really fix it before it really collapses. So that's kind of a predictive analytics which is really going to help in a lot of use cases. Security suits, that's again a huge amount of revenue streams which 5G is would be getting into. So $5 trillion business is what this major five entities constitutes: manufacturing, transport, construction, utilities, and mining. If you really see this, this is the present scenario of some of the sectors, and if you really see, this is where the future is. The second, the pie chart is the future. So if we just take the transportation, this is going to be taking it to a 659 billion kind of business into these. So not only this, there are more use cases, but these are the five major revenue streams which would flow in the initial stages of 5G, is what it is predicted. So 5G trials worldwide. Unfortunately, you cannot see India colored here with trials. So if you really see, there's a reason why that is. India is also doing, there are a lot of OEMs like Ericsson, Nokia, India as well contributing for this. But why India does not show it up in this map? The reason is a lot of innovations or patents are not getting registered in India. There was a forum which I did attend where the government of India stresses more on to locally registering these innovations. Whereas compared to China, China has hundred thousands of patents which is getting registered under the 5G trial. But India, most of them gets registered into the international market. Yes, there are reasons where these patents get more secured enough. And to a statistical way, it was in the mid of 2018, June, July, it was 7 patents and 11 patents in two different scenarios where India is just compared to thousands of patents which is getting registered like country from like China. So that does not show that we're not innovating. So the GDP of India as a country, how is it going to grow? Today at present, the operators produce a GDP of 0.63%, and from a mobile ecosystem, it is a 0.08%. This is expected to grow a huge amount. 6% of the GDP is going to be from the the post to the 5G launch is what India predicts, and it's a 14% of year-to-year growth is what it is expected. Now coming to a little more of technicality, 5G architecture. So we have seen this diagram in another fashion. So the enhanced mobile broadband, ultra low latency, and mission type of communication uses any of these entities. Like say for example, the yellow piece of information which you say mobile. Massive mobile type communication. This looks of more of densification and area traffic capacity. Let's not say that it does not look for the other. These are the major things. From an ultra low latency, it is latency and mobility for services like mission critical services, and hence mobile uses most of these comparatively. So this is an architecture where we have the core and the radio in a very high level form. We have femto, pico, and mission to mission kind of a gateway, device to device relays. All these are under the radio, getting connected to the core. And from the radio, we have a lot of applications which gets connected, like smart grids, vehicles, virtual reality, industrial. I would not talk of much of this here because we are going to be seeing a lot of use cases onto this. Smart grid, yes. With the 5G evolution, a person who is going to be using electricity can be using at the best effective way of using the smart grid under the 5G. Now, under the power reduction, this is again a very high level. So we have seen a transformation from 1G, 2G, and towards a 5G. So when we see in the technologies like 1G or 2G, they did not much bother about power. So what it was, the RF module and the system module, which is the baseband unit, were both clubbed together, and the air cons which were used to pump in to maintain the temperature was much heavy. So that has nothing to do with power reduction in these technologies. When we moved into a technology like a 3G and a 4G, what we did is we did move the RF module close to the antenna, still maintaining the baseband or the system module at the base station. So it was a 40% reduction from the previous generations. If you really see from a 5G point of view, even the baseband unit or the system module was made at the cloud. So this reduces, expected to reduce a 60% of reduction in the power. So if you see from a traditional and a cloud, a little box shows the power. So if you see from a traditional point of view, it is 2 kilowatts is what the power which gets consumed from an air con. And from a cloud computing, it reduces to 0.1. That means I do not have much of entity to make it cooling, where I'm going to be using air cons or eventually the power. So from a traditional 3.45 kilowatts, the cloud radio gives me a 0.86 kilowatts. That's a huge amount of power saving. This is another way of looking into it. This is one of the operator, where they have 830,000 BTSs under 2G, 350,000 BTSs under 3G, and 800,000 BTSs under 4G. To give you an apple-to-apple comparison, close proximity, 2G and 4G, when you take, it is 80 gigawatts of gigawatt hours of power which the 2G converts, whereas compared to a 16 gigawatts of power in 4G. So if you take a per BTS, it is 96 kilowatts per BTS, which is dropping down to a 16 kilowatts. And if you see 60% of reduction from this, again it is 9.5 kilowatts of power, which is going to be reduced in the coming technology like 5G. So base station becomes more power efficient. And from a capex and opex point of view, from an operator point of view, if you really see from a capex, the air condition uses 51% of the power. Equipment, it is 46%, and the others is 3%. That's a huge amount of power which is the aircon consumes. And from an operational cost, it is electricity 41, O&M 21, site rental 31, and transmission, which is 7. So the operator who really encashes his business by selling electromagnetic waves, it's only 7% of the operational cost. The remaining 41%, a huge amount, is from the electricity to pump in these air cons. That's where the reduction can be. So the deployment becomes much cost effective comparative to the previous technologies. So this is an LTE architecture when we're comparing to a 5G kind of a scenario. So what you see here is the E-Node Bs, which is getting connected to the S1 user, S1 MME. And what we see a shift in 5G is the control plane and this user plane are separated here in the 5G kind of a scenario. And the user plane where we have SGW and the PGW would be replaced by a unit called as user plane function, UPF. And the AMF access and mobility management function is the AMF, which replaces the entities, like it's going to be consolidated of the MME and the HSS and the AA kind of a scenario. And from this is from a core side. And from a radio side, we have the G Node B, which is going to be the 5th generation based transceiver stations. And this one also have an evolution from where we have split the transport layer from an RRU and BPU, and hosting this BPU more towards the virtual core. So this is another way of looking into the architecture, where we have the G node B and the new generation E node Bs, where LT pushing towards 5G. So what does that do is the G node Bs gets connected to the AMF and the UPF. So the G node B provides the protocol for the user plane and the control plane towards the UB, similar to the new generation E node B, the LTE. And this is how the G node B would communicate to the AMF using a new generation control plane and a new generation user plane, similar to the LTE extended kind of an base station. So these are some of the aspects to read through. Just quickly go through this. The G node B or the next generation E node B, it's going to be used for radio resource management, where radio bearer or radio admission control, RAC and RBC, is a subfunction of this, where this is going to be helping the establishment to be rejected or accepted. And then you have IP header compression with an IPv6. The header, are huge in number comparatively. This is done by the G node B. Selection of an AMF. There are instances where the UE is not able to communicate to the G node B of the selected of these AMF to be selected. So that gets selected by the G node B from the list of already listed AMF. Routing of the user plane data towards UPF, routing of the control plane towards the AMF, connection setup and connection release, the CR and CS kind of an application, scheduling the and transmission of the paging message and the system broadcast message, network slicing. Network slicing is an important concept in 5G, and the G node B does it at the radio level. Similarly, there are other entities which does it. We are going to be seeing at the core level. QoS flow management, and from an AMF. Access and mobility management function, the non-statum signaling which between the core and the UE, the core network node signaling for mobility between the 3GPP access, idle mode, UE reachability, registration area management, inter and inter-system mobility. Then you have mobile management control, and this supports the network slicing at the core and the SMF selection. So this is in a nutshell where we have the G node B. We did speak of the G node B. We did speak of the AMF. Then you have UPF, which does the mobile anchoring and PDU handling. Now from an SMF, which is the session management function, this is the one which UE IP address allocation is done, and PDU session control. Now this is a very high level again. So this is where the leftmost corner, the red one, is the UE. I have the air interface, which it gets connected to the antenna system. Then I have my transport layer. The transport layer is again broken down into the RRU and the BPU. Depending on the kind of slicing, I would manage with the kind of applications which would the system would demand. These are the protocols which we have, which is the RF, the physical MAC layer, lower and the upper, the RLC, PDCP, and RRC. We're going to be seeing one new entry of the protocol, which in the coming slides. And from a user plane function is where you have the UPF. We just now saw the applications of AMF and the SMF. Now coming to the NSSF, this is the entity which takes control of the network slice selection function from the core. The NEF and the NRF, which is the network exposure function and the network repository function, these are the ones which is the data engine to the control plane, where the data analytics really resides on. Then you have what is called as the PCF, which does the policy control function. All the policies are controlled by this function. Then you have we see the UDM, Unified Data Management, where the user identification, SMS management, and subscription management of an activity is done. Then we also have an AF, which is called as an application function, which does the route the traffic to and the policy control towards the further entities. And we also have the authentication and the service function, which does the authentication not only for the 3GPP, but also for the non-3GPP kind of a functionality. So this is the 5G, the RAN architecture. So I did speak of, just to take one OEM here, I've taken Ericsson here, where, Ericsson promises to, attain high data rate. And here, how they're going to be doing this is using the front hall at the radio to have a different architecture. So we have distributed architecture, centralized architecture, elastic and virtual architecture kind of a thing under the RAN. So here Ericsson comes up with a front hall 6:2:2 kind of a front hall, where it can have 18 transponders kind of a thing. That means 18 radios encapsulated into one unit, and this is 6 to 9 times higher capacity than the LTE at present. And we also have the front hall 6S81, which is the passive filter, and this filter can combine these radios to a grade of 24. So how is that going to be helping us? Is say if I have to have a fiber kind of a connectivity, I can combine this and still give this kind of a services. I can go from a 24 to a 48 and so on. And what they're also working to have high data rate is a transport layer. What we've seen for CIPRI kind of an architecture in the starting of the 3G towards 4G. So this is going to be evolved to enhance a CIPRI, eCIPRI kind of architecture, where the capacity, latency, and reliability is taken care of. Now, in scenarios where my connectivity, the last mile cannot be achieved, it's difficult to achieve conventionally. I can use a microwave front called 6392 from Ericsson. This promises to connect with a 10 gigahertz of connectivity. It works on a CIPRI with option 7. We'll see what option 7 are, and can expect it to go for the 2 kilometers of range. So the last mile, which was a difficulty for me to connect, can be enhanced for this. So this is where, in a nutshell, the high data rate, one of the ways where Ericsson promises to enhance. The two major aspects in 5G, the 5G new radio and the frame structure, is what we're going to be seeing next. Sorry. The 5G new radio promises 4 windows of opportunity. One is the massive MIMO incorporation, millimeter wave, multi-RAT, and wireless network. So when we talk of the massive MIMO, it is more to do with coverage and capacity. We have beam scanning, beam forming, beam management. So beams are so powerful that it can trace a user. It can change the angle, to exactly pinpoint the customer and track him during his mobility. We have 64 as we did discuss that this was tested recently, and 256 or 256 planned. 3D MIMO is another version. Millimeter wave, yes, this is a high frequency, and that's a huge amount of spectrum which is going to be made available, smaller wavelength. And this smaller wavelength constitutes for small kind of antennas. So that makes a huge amount of antennas that can be, accommodated, into a 5G kind of a scenario. From a spectrum point of view, where we have a cellular 780 megahertz of cellular spectrum, this is going to be enhanced to 60 gigahertz of unlicensed spectrum under the millimeter wave. Multi-RAT, where we have multi-users, we did see how each vendors can accommodate their radios into base stations of another OEMs, so more flexible. Evaluation of the existing RAT, existing cellular for 3G, new access technologies, millimeter wave, Wi-Fi, Bluetooth, low energy, these kind of things emerge under this multi-RAT. And from the 5G new radio, we have the wireless network, where the throughput in the downlink is expected to go to 20 Gbps, and the uplink to a 10 Gbps. And how are we good doing this? Densification of a small cell. We have a lot of densification, architecture models which are getting developed under 5G. Network function virtuality, software-driven networks, centralized RAN, where you can take the BBU, more towards the core side or virtually. The C and the control and the user plane separation, splitting the RAN network slicing, which can happen both at the radio and the core. Dual connectivity both to the LTE and the NOI radio, and the self-optimized networks are some of the entities which comes under the 5G. So these 4 things, massive MIMO, millimeter wave, multi-RAT, and wireless network entities become the main pillars for the new radio under the 5G. This is another way of looking into. So this is where I have my RRU, which does the modulation and demodulation, and I have the baseband unit, which does the signal processing. And in conventional networks until 4G, we were using a transport protocol called as a CIPRI. And what does this CPRI do? Each of these antennas, you would have a CPRI protocol running into a cable. So when I have massive MIMO kind of a scenario where 64 cross 64 and much more, I cannot have so much of cables running from an RRU to a BBU. This was one of the limitations where it pushes the technology to move to an eCPRI kind of a thing, where it looks into Ethernet and as well as IP. There are other entities like NGFI, which is the next generation friend call interface. We also see the new kind of a protocol entity which is added in the 5G, which is called the SDAP, which is called the Service Data Adaptation Protocol. What this does is it does the mapping of the QoS, quality of services, to the data radio bearer. So based on my quality of services is what the service would be allocated. So that's the main addition from a 4G kind of a scenario, and as well as the RRU and the BBU, where it gets separated depending on the kind of services the split would take in. The layers are called as F1, which is the BBU and the RRU, and the F2 is the kind of an interface which is the eCPRI kind of a scenario going towards the connecting towards the antenna system. So this is where the CPRI, eCPRI, and the NGFY works in tandem. So see, if CPRI, this is not suitable for a multi-vendor kind of an environment, and it is a point-to-point kind of a design, priority, and then it's only Ethernet and a high data rate. So when we go of an eCPRI, it works both on the Ethernet and an IPv, probably the IPv6. Low data rate overhead because of the IPv6, a lot of data compression can be achieved with this. Not suitable for a multi-vendor still. Point-to-point and a point-to-multi-point kind of a communication is what the eCPRI believes to. Unfortunately, the eCPRI, which comes from the same family of a CPRI, is not backward compatible with CPRI. Coming to the NGFY, this is surely compatible with the CPRI kind of a protocol. Point to multi-point, then you have this is an open source, anyone could get in. I mean, if a vendor would want to get into the NGFY, he can use the coding and then move it. Ethernet, low data rate, and multi-vendor possibility. That's a beauty of the NGFI. So it's a battle between the eCPRI or the NGFI, which would take in to the protocol, the transport protocol. Moving into the waveform, the 5G uses the CP-OFDMA, cyclic prefix OFDMA, in a scalable numerology, both in the uplink and downlink. What scalable numerology means, like say what we've seen with the 4G kind of a scenario, these frames were fixed. So I did not have options of flexible frames. So here I can scale these numbers according to my services. The design is simplified because it uses both in the uplink and the downlink the same waveform. And also for coverage limited scenarios, it goes to use a DFT SOFDMA, which is discrete Fourier transform spread OFDMA. Now moving on to the frame structure, to start with, it is the same frame structure of a 4G. So 4G, one frame structure which has 10 slots. Each of these slots are called one subframe, and the total width is 10 milliseconds. Each of the subframes are 1 millisecond. 14 OFDMA symbols get accumulated into each of these slots, similar to that of the 4G. And then OFDMA symbols, I can, along with this, I can use the subcarrier spacing of 15, 30, 60, and going forward. This is the change, which gets in with 5G. So this is how the calculation. There's a little formula, delta to the power of mu into 15 kilohertz. Putting in these values, you can get in a different, scalable numerology to achieve. This is what we're going to be seeing here. So the first one, which is purely a 4G kind of a scenario. The second frame, which you see, again, that's a 4G kind of a scenario where the 5G is built on that. So one times for the blue box, which you see with the number 1, this is 1 milliseconds, and it has 14 OFDMA symbols with a duration of 0.071 milliseconds. 15 kilohertz is the bandwidth. Now, in spite of accommodating 14, OFDMA symbols into one subslots, I can do, double the number, 14 for first 0.5 milliseconds, and another 0.5 milliseconds, I can accommodate another 14. That means this increases it decreases my latency from 0.036 milliseconds and accommodating 30 kilohertz of bandwidth. So this is where the scalability really moves into. So if I have more number of, say for example, for a 60 kilohertz, I can, have 4 sets of 14 symbols accommodated with a duration of 0.25 milliseconds, and going forward to 100 120 kilohertz, 240, and the last one which shows for a 480 kilohertz. So this is where there is a flexible frame structure which the 5G promises. And how is this going to be getting applicable is in a 15 kilohertz of a scenario is what the plain 4G sees, and in a 30 kind of a scenario where I have a slot say 500 microseconds I can use for an enhanced mobile band broadband kind of a communication. Now 70 microsecond I can use for an ultra low latency mission critical services kind of a application. Going forward to a 60 kilohertz, I wanted something which has to happen very quickly. I can still use subframes at 35 microseconds for an ultra high ultra reliable low latency kind of a communication. If I have to accommodate more kind of a data into that, I can use an eMBB combining more slots. So each frame is flexible, automatically with the kind of service requirement. So this is the beauty of 5G, which was never there in 4G, where these slots were fixed. So moving on to the 5G use cases now. Okay. So I have a couple of things where we would walking through from a use case. So especially I've taken as a couple of use cases more to do with it's a mix of an IoT, data analytics, all under the 5G. So connecting anything and everything. So that's where the possibility the 5G gets into. I can connect goods. I can connect people. I can connect. Objects around me. I can connect machines. I can connect, appliances. The 5G promises to connect vehicles. The 5G promises to connect to a couple of buildings, and it promises to connect soil. We're going to be seeing use cases how soils are going to get connected, connecting animals and connecting, plants. So 5G promises to connect anything and everything. That's the beauty of 5G. So we're going to be seeing each of these a little use case where it can really show you the applications into these. So connecting goods, Amazon. I've taken an example of an Amazon. So, say for example, I'm a user. I use a particular goods, and my usage is for a duration. Say for example, I use toothpaste. I use toothpaste, and it lasts for say 20 days. I have a 4-member family, and the usage is for 20 days, and every 20 days I make a purchase. So Amazon keeps tracking my purchase. So what does it do? Ultimately, it knows that by the 18th or 90th day, there is a trigger that I will buy this product. So what Amazon is moving in is to ship this product close to the the retail or the wholesale kind of a place where the customer, close to the customer, in fact, where he can accumulate. If my predictive analytics shows that the customer is bound to buy, I also go to the extent to ship this this product in advance to the consumer. And the consumer is surprised, someone knocking at my door and say that I have something for you, and I will not deny because I have that's my need. So that's the kind of connecting goods. Now connecting people, so the kind of a Google, if you can see here, we have been Googling where, where the cafe coffee day is, where Pizza Huts are, the future is where my kid is, where my dog is. These are the kind of, connectivity which promises in the future. And also we would be able to connect the internal parts of a human body. Say, for example, the stem cell. So people who have stem cells stored, and a user who would want to can really touch base understanding from the database worldwide. And for example, in countries like United States, what happens is if we go for a medical treatment, they would also compare your DNA and where is this DNA originated from. And say for example, the DNA is tested for that individual, and it turns out to be from an X country. So what happens is, oh, this X country are more prone towards heart attack. So proposals of having more D can reduce the kind of heart attack into these kind of people. This is the kind of evolution where connecting human internal parts can help with the 5G technology. Now moving on to objects like umbrella. These are IoT sense umbrella, where we have the umbrella gets connected not only to your devices like your mobile, it also gets connected to your weather forecasting. So today, if it is going to be raining, the umbrella can, if I have forgotten or if I do not know whether the weather condition, I've not seen my news in the morning. So this can alert that it's going to rain, you have to take me. It gives a buzz onto my handset stating that, because it's already mapped with the weather forecasting that is going to rain. That's the kind of an object where it can get connected. Missions, it's going to connect all of industries. Dark office is another concept where the future of the offices are where it's expected that machines would take over a lot of jobs, is what the conventional way of doing jobs. So there are new jobs which is going to get created, in fact. But then the dark office is where I would not have the need of, as an entrepreneur, to lighten my office, do the interiors, waste a lot of power to light up. I can make the machine work day in and day out without a single bulb, hanging in the office. That's a kind of a dark office which reduces, promises efficiency, and machine does not require light or air conditions or heaters, as a human being. So that's the kind of evolution where machines are going to get into. Now moving into appliances, mobile getting connected to appliances like refrigerator. Refrigerator can also understand your buying potential, your consuming potential, and it can go to an extent that it can order from a supermarket if things get go out of stock. Moving on to vehicles, so this is a beautiful, in fact, use case. I've taken Nevada, United States, where the road traffic control department, what it does is there are around 1,100 plus of traffic signals which gets connected, which are already connected onto data analytics kind of a friend. So this captures the signal, this captures the traffic, and these data is analyzed to control the signal. So like what we have a conventional say traffic signals in a crossroad, where these are set to a particular fixed time of say 30 seconds. Rather, these would move in with the requirement. So, for example, there are emergency vehicles. It would give preference to that. If it's an office time at 9 o'clock and there is one lane which shows that there's a whole lot of heavy, vehicle, but the count is only 10. That means that is a road which is not required to get open. Give a priority to an office kind of a road which is at a 9 o'clock, which requires more attention. So that's a kind of a control where these signals would be. And going forward to a next level, the automobile company like Audi, launching its Q8 kind of a vehicle. What it does is it goes and subscribes these data from these road traffic control and buys this data. So when a gentleman buys this car, you have an option of subscribing this data. And if you subscribe this data, if it is an unmanned car or a manned car, it gives you, say, if you're standing in the signal, and if the signal is followed for 120 seconds, it can contact, this car can contact the traffic signal and say that in spite of waiting for 120 seconds, you can take a left or a right, a free light right to the left, and then still reach the destination with a lesser time. Or in fact, the vehicle also gets to the next level. This is already there. So moving forward, the idea is like, say for example, a gentleman traveling, or I travel onto this car and I'm waiting for a signal, and the signal is 120 seconds. Now my vehicle is in touch with the infrastructure around me, and it also knows my spending scenario. It knows that I withdraw cash every 20 days or 30 days. I withdraw cash, and it knows that I'm almost not withdrawn for the last 20-25 days. And it finds an ATM which is close by. The car is already communicating with the infrastructure like an ATM, and it shows that the traffic inside the ATM is also low. There is no much person, and the signal which is fallen is 120 seconds. So it gives me an instruction that, hey man, you can you are in need of money. The ATM is free. The signal is for 120, and it helps the user. So that's a kind of an evolution where the vehicles are, moving to. It's the V2X kind of a communication under the ultra low latency kind of a communication. Now, buildings, house automation, as we have, most of you might have seen, house automation is coming in a large power grids, where I can, have my washing machines, instructing my washing machine to switch on, where which is the most cost effective, maybe in the middle of the night at 12 o'clock is where the per electricity rates are low. It would, start on and save my electricity bill. So these are how buildings and things gets connected. Now, this is again an interesting thing. Now, this is how we are connecting soil. Uh, this use case is very much in and around the outskirts of Bangalore. In fact, there are financial institutions which uses technologies at present, which 5G is going to be more accelerating, is what we see. How does what does it do is say I'm a farmer who has asked for loans to buy fertilizers, and I have a field, say I'm growing paddy, and the paddy is these plants are only 2 centimeters above the ground, or say maybe 5 centimeters above the ground, and I've asked for loans. So what does the bank do is they send drones to the field, clicking photographs of these crops, and it also sees what is the health of the crop from the image processing. What it does immediately when the images are taken, these are sent back to the server. No, middleman intervention. It also drops in to different parts of the field and measures the earth precipitation, how the earth is fertile, and this data is sent across. So before the drone reaches, the bank already has the kind of potential growth what the soil can give. Then it also it also combines the weather forecast after 2 months, how things are going to be for the next 2 months, where the crops are going to be ready. Demand is, am I the only farmer who's growing, or do I have a lot of demand, but the supply? So based on this is what the loans are sanctioned. This is really happening since last more than 6 months in and around Bangalore with lower. So this is going to go accelerate, much more with 5G kind of a scenario. Coming to a pesticide kind of a thing, so if a field is infected by a pesticide, I would not want to, spray pesticide to the whole field. So a heat map kind of a thing can be generated, and use pesticide control only to those places where it is affected. That's the beauty where things are going to evolve in the coming futures for 5G. Animals we can connect, so this is again an IoT, but then it is based on the IoT presently. So what this is again in the outskirts of Bangalore, say the forest area, where electrical fences were laid to block animals reaching human inhabitants. It was killing. So these were huge animals like elephants. Also, the smaller creatures were under threat. So what was done is there were sensors which could sense the size of an object, what is the kind of an object, and electrocute that fence accordingly, so that it just leaves a shock kind of a thing. So this is again communicated back onto a network. So this is the a case from an how we're going to be connecting animal and reforming their life. And plants, your kitchen garden, when you go, that's again we can connect it to a narrowband IoT under the 5G. Ecophony is growing fish and plants. This can also work with IoT devices which can be connected to the 5G kind of a network. Now, coming to a concept called CCN, which is a customer-centric network. This is a shift what we are going to be having from an IP. So, if you see the little two diagrams towards the bottom of the slide, the conventional IP network, the user would, ping in. Say, for example, I'm searching, Cafe Coffee Day. So it would hit the Cafe Coffee Day server and give me what is the location which is close to where I am. So, all the way it would facilitate the routers, and the user gets the information. This is a conventional IP, whether it is IP4 or an IP6. But in a customer-centric kind of a network, what happens is the user immediately when it pings the router, if the router already has this information, it is going to cache from that. It is not going to be, touching the web server, a long way. If it does not, it goes to the next router and next router, and until it reaches the content. So once the content is received from the entity, it keeps feeding in to these routers so that it can be in the future available. So this is a content-centric network. So it's a shift from where we are having from container to a content kind of an approach is what we are looking. So if you see from an Ericsson point of view, I've taken Ericsson as an example here. It's called as a user data consolidation, which is the same kind of scenario we use as CCN kind of a networking. And what is this going to help is this helps high scalability, manage better resources, manage better congestion or load in the network. Using the CCN is what some of the cases I have. So today, in a conventional way, network, what I would travel in morning to go to my office, and what I do is I keep downloading music. It's a kind of a regular music which I am used to, and then the system knows what music I'm downloading. In a conventional way, what it is, it checks the resource availability. If it is congested, I do not get that. But using a CCN kind of an approach in a 5G kind of a scenario, since the music is the same thing which I'm downloading, it's on a daily basis, and it's the same path which I'm taking. I need not to go touch the server every now and then. I can cache it from the router or the site which is close to it. That's the beauty of the CNN, which can enhance the customer experience. Now, moving to another use case where this is a high-end user. The high-end user can be separated from a quality of service, a quality of service from the other user. So if I have a lot of users, I can separate him, and even when there is a difficulty onto the network, I can heal the network as soon as possible in a 5G kind of a scenario where the customer is really not aware of the problem before it is fixed. Now, this is a use case where it's a smart city kind of a concept which is under the 5G using a CCN kind of an approach. So I have a scenario where retrieving the lost object from these network. So what is my aim is to retrieve a physical object which is lost is what I'm trying to do. So what I do is what basically is required is all the objects which is to be retrieved has to be tagged. There's a tag ID which is facilitated. It is maybe during manufacturing or at the later stages. And when me as a user, if I have lost an object, as an owner, if I lost an object, I would notify the server by the tag ID through the service platform. The service platform can be a web site, and once it goes to the website, what happens is it sends message to the CNN-based network, and at the CNN-based network, what it does is it's update and register a table called as PIT, pending interest table. So this pending interest table keeps track of that there is a pending task which is there until it is served. So anytime when a sensor, the end sensor receives this tag, it intimates that the coordinates back to the user that this is where the location of the object is. So any object which can be lost can be retrieved. This is for a scenario where it is within a city kind of a thing. Now moving on to another kind of a scenario where I have lost an object in city A, and I would want to retrieve it from city B because the person who's stolen is moved out of the city. So what happens in this kind of a scenario is the service platform contacts both the city gateways using an IP address. That's the red lines from the service. You have Brest and Lennon is the two cities here as an example. So once this goes, the IP address, the city gateway, converts this IP address into the interest messages, which is stored on those tables. And as and when, whenever these IDs are sensed by these IoT devices, the end devices, it would, communicate back to the service platform, where the service platform can be a 5G network. This is how a lost kind of an object use case can be seen. This is a GUI where you can see where the object is lost. So this is a portal. This is a graphical user interface, and this uses a MongoDB kind of a database. Why MongoDB? It's an unstructured data, because the kind of data which the sensors would capture. It could be a video, it could be a photo file, web page, and so on. So this is how a user can really detect a lost item. And this is why a movement of smart city or smart homes is becomes important. These are some of the statistics which shows Earth land taken by cities is a 2%. Global population living in the city presently it is a 55%, little more than that. Global population living in the city by 2015 is a 70%, and the mega cities at least 10 million inhabitants by 2030 is a 41%. Global energy usage and the carbon emission is a 76%. So you can see this number. Global GDP growth generated by 600 large cities by 225 is a 65%. So that is a huge amount of potential to make cities smarter, or homes smarter at the urban front. This is again a video. I would send across this link where a smart city kind of a concept is explained well. You can see it post this session. 5G optimization. I know it's too early to speak of optimization at this level, but then I still have taken a narrowband IoT kind of a scenario here to easily explain you. These are some of the the objective of an NB-IoT: improve indoor coverage, support massive kind of a MIMO, reduce complexity, improve power efficiency and latency, as we all know. So improve power efficiency is where I would take in the narrowband IoT is launched under the carrier or the carrier IoT is launched under the 5G is what we believe. Or you can also take a scenario where the legacy network like a GPR as a 2G or a 2.5G kind of a network is used to communicate a massive type communication. So let's take an example of a GPRS. So in a GPRS kind of a scenario, what happens is here, in a GPS kind of a scenario, we were not bothered of the battery life of the devices, but in a massive mobile type communication, this is expected to push years of battery life, 10 years plus of battery life. That's a huge amount of battery life. So what can we do for improving this power efficiency? There are, power saving, state which can be achieved in these, in this scenario with the release 12, where if you can see the slide here, whether it from a transmission to a reception and at the idle stages, so we are going to be operating much below that as the power saving state. So when we do this, these battery lives can be enhanced in mobile type communication compared to the legacy devices under the GPRS. These are some of the parameters which you can fine tune, whether the battery capacity can be fine tuned, battery power during the transmit, battery power during reception, battery power when idle but not in the PSS, and the number of reports per day, and so on to read for. We're going to be taking these as an example and see how we can calculate for a quick, not going to take much into calculations here, but then to explain you mobile to mobile device kind of a thing, how battery life can be calculated. So I'm going to be seeing how much of energy is going to be consumed per data report. So this is where you have an energy of transmitted, received, and in the idle stage. So number of events, I multiply that, I get 0.00006 is what the joules of energy consumed per day. I have how much of reports are going to be sending in a day. With that, I get 0.12 energy, and days of battery life. So the battery energy capacity I've taken here is 1. That divided by the total energy consumed, I get 69. So when I divide by 365, it's a 2 months of battery life is with the scenario of these parameters which we saw in this slide. When I take this and put in here is what I get. Now, how can I enhance this? If I use the battery energy capacity from 1 to increase it to 5, so that's where I get this. So if you see a little rectangle blocks towards your right, this is a 5. When I put in 5 as my battery energy capacity here, I get 347 days. That's most close to 1 year. That's the amount of push where we can enhance the battery life in a narrowband IoT kind of a scenario under the 5G. Now, similarly, people who have worked with timers, say, remember, GPRS timer T33414. This is the same timer which can be enhanced here in a conventional in this scenario, where typically this takes a value of 44. This can be reduced to a 20 seconds, where accommodating low power for a mission-to-mission kind of an device communication under the carrier IoT. Now, this is also called as a ready timer. What it does is it transition from an ready to a state monitoring is what it does, and it only performs a routing area update during this. So we have a maximum value of 1111 followed by a few ones and twos, and then a minimum value of 2. So if it is set to a maximum value, then the ready state is on. When it is set to a minimum value, which is V0, the ready state is off. That means power saving can be done, and the enhancement of a battery can be done in this mission to mission kind of a communication. From a GPRS point of view, it is a 44 seconds slow transition from a ready to standby, and a mission to mission, it has 20 seconds, which is a quicker transition from a ready to a standby kind of a scenario. Well, now we're going to be seeing how the 3GPP 22.862. This is one of the latest releases, which was released way back in July 2018. That is 2 months ago. Under the ultra reliable low latency communication, we're going to be seeing some use cases here. Before that, the mission critical service is one of the main thing which the ultra reliable low latency deals with. And when we see that there are three, main criteria which it supports: low latency, reliability, and availability. Low latency, fast enough to communicate; reliability, the number of packets which is successfully delivered to the total number of packets sent across; and the availability, the percentage of time the 3GPP system delivers services to what is expected to deliver. So these are the three entities which the mission critical services the pillars for. And the ultra reliable low latency use cases are expected to fall under these scenarios. It can be high reliability and low latency. It can be high reliability with a high availability and low latency, very low latency, high accuracy position. We're going to be seeing some use cases, especially under the high accuracy position, high availability, and mission critical services, obviously. So URLC use cases. This is with high reliability and low latency is what it expects. Quick communication and reliable communication is what it is expected of URLLC. Now under this, we have one of the use case is power plant. You know, the network slicing, where we have seen that it can be done at a core and the radio level. So network slicing can isolate a traffic and still give high reliability and low latency for this kind of an application. We also have another use cases where virtual communication. So virtual communication today, say for example, you can see my screen, you can hear me, but you do not have an effect of 360-degree. So you do not feel a classroom kind of an environment or a one-to-one kind of an interaction in today's session. So this can be enhanced by a 360 virtual communication, where you feel that you are interacting to the tutor, you are interacting to your fellow mates who are sitting far away from you. So this is the kind of a communication which can be achieved by high reliability and low latency under the URLLC kind of a communication. Then I have use cases which is the industrial factory automation. So under the industrial factory automation, we have two cases which I'm going to be speaking on to. First is a factory, and then I will move on to a plant. So factory is a smaller entity compared to a plant, as we all know. So this is a closed loop of an environment. So we have especially these controllers. These controllers are the ones which would instruct these sensors. There are a couple of sensors. You can have hundreds to 300 kind of numbers of sensors or actuators. So these controllers would instruct these sensors to measure the data or actuators to act upon a task. So once they do that, they would respond back to the controller, and it is in a closed loop of an IoT-based kind of a it is IoT-based kind of scenario within the portfolio. And here, the density of these sensors actually is 1 per meter square is a kind of scenario what we have. Now moving on to a little more at the next level, where the plant, which is a bigger entity, where I have thousands of sensors which it can accommodate, and it is expected to have a packet loss of less than 10 to the power of -5. Is this kind of a scenario? Here, this is where I have this is a 5G kind of a node B which gets connected to the process controller, and these process controllers have different nodes like which control the sensors and the actuators. So this is an interface to the larger network like in 5G, and it works on an open loop control application kind of a scenario. So that is where use cases can really come in. Now, using the ultra reliable communication, this is one of the use cases what we have, pushing the television, technology to the next level. So, if you see here, we did the start off with an SD, fully HD, 4K, 8K, and moving towards a 16K. So this is how the picture you would look. These are the pixel, vertical and horizontal pixel, which you see for SD, full high definition, 4K ultra high definition, 8K, 16K, 15360 vertical pixels to 864 horizontal pixels. So what is this really getting in? The ultra high density kind of a communication, it's giving a video quality, and it is increasing the frame rate to 120 frames per second, which presently is only 60 frames per second. So what eventually is going to happen is with a 4K, if you see a little window towards the rightmost, a 4K can give you a screen size of 40 inches to a 65 inches of a television. This is going to be pushing to a 65 to a 95 inches with the 8K, and much more with the 16K kind of a scenario. That's evolution which the 5G takes care under the ultra reliable communication. If you see from another angle, this is how the pixel point of view it looks. So if the rightmost is the 4K, where you do not have a differentiation of color, 8K you still have more details into it, 16K further more details into it, making the quality of pixel much better. Now moving into high reliability and high availability, and also the low latency. This also promises quicker communication and reliable communication. Here, network slicing again plays an important role here. Drones are some of the examples which I have taken here. High reliability, high availability, and low latency can be achieved are required for applications where the drones would be used. Industrial control applications, they also use the high reliability, availability, and low latency kind of a scenario. Subject to in a conventional way, there are more subject to tear and wear in an industry. Because of the wiring, the mission designs become so complicated. I do not have 100% of a mobility. All this can be achieved by a 5G kind of a scenario where the mobility can be done, and eventually the efficiency of that industry or the factory can be achieved, with high reliability, availability, and low latency under the 5G. These are some of the examples which are the use cases which the drones is expected to come. Aerial photography is one thing. Then we have film and TV footages, which is going to be taken by care using the high reliability, availability, and low latency. So this is the aerial mapping, which can be done like what we do for a Google Earth kind of a thing using satellite. This is archaeological sites. Archaeological sites looks, when the archaeologist starts digging, an aerial view can give a better picture of the archaeologist site, design of these sites. And this is already proved in some of the countries where they have used drones. Then you have marine wildlife. You can see a baby blue whale with his mother. So these kind of images were never possible to take. So marine wildlife can be better studied. This is again what you call as poaching, where this can be better tracked by drones to eliminate these kind of activities. Then coming in a little more is a meteorological monitoring where drones can be used. Then we have filming, crime scenes even before the officials reach there. So these drones can fly and get these images before the really the police reaches there. Yeah. And real estate, it gives a better view of the house, which is as shown in the picture. And it is also proved that the sales of these houses have much better yield profits compared to taking photographs at a ground level. Now, search and rescue are another kind of an application which comes in. Domestic roof inspection, these are very delicate roofs which can be cleaned using drones. And solar park inspections, so each of the solar grids can be inspected one after the other, which would take man days for manually doing it. This can be done by drones. What would be required? All this is a high reliability, high availability, and a low latency kind of a communication. Now, moving on, drones, we would be using it for delivery and medical supplies, which becomes news filming, then pipeline and power line inspection. So it can run through to understand any leakages, which can be done in minutes, and also the tunnel inspection. So this is a kind of communication which is available with the URLLC kind of an communication under the 5G. We also have some more things. Okay, agricultural pest control, which we did discuss. If so this heat maps which shows the blue are the where pest affected. So we can use drones to get rid of the pest only at this, in spite of spraying the whole field. So that's a kind of an agricultural pest control which we can use. Then aircraft inspection, from the tail to the nose of the aircraft can be inspected in minutes compared to manually doing that. Then internet access, yes, in urban places where internet becomes difficult to cater, and it is for a temporary kind of a thing. You can have drones facilitating internet. Say for someone wants to use it for 2 hours, the drone is facilitating you, and then on a paid kind of a service. That's the amount of access which we could give. Wedding photography, which most of you might have seen. This is the latest entry onto the drone, where the movement is through the eye movement, where the drones are controlled using the artificial intelligence is what it takes in from NVIDIA. Now, using a very low latency, again under the 3GPP URLLC, we are seeing virtual reality, some of the use cases under the virtual reality. So virtual reality promises very quick communication between the sender and the receiver. And so we have applications like remote surgery. The remote surgery, is expected to go to that level where the doctor can, feel the thickness of the operating thread remotely, so that it takes care of the skin during operations. And virtual reality is another great innovation which can be achieved with very low latency kind of a communication. And this is the virtual reality gives a sense of touch, which is called as a tactile kind of a thing to the internet. So that's again a new kind of an era which is going to be opening up an opportunity under the very low latency, under the URLLC kind of a communication. So these are some of the use cases good to know. So we have virtual reality where space exploration. NASA is working on Mars exploration by 2030, where you can have better simulated life on the planet with better accuracy. So you're having a VR headset, you can virtually explore the moon or the outer space, which is not possible for a common man. Surgery, from a surgery point of view, this is another example using virtual reality. See, a medical student goes into intensive kind of practice for long years, of surgical trainings. This can be substituted by the virtual reality, and in a controlled and a safe environment. So what is this going to give is, we are not, these students need not work on a live patient, so they can have virtual reality to get that experience. So better life or better surgeries can be done. Military training, one out of the 20 soldiers died during training, is one of the use cases which most of the countries says. This can be avoided by VR, having a combat environment created, which is more safe, for training facilitation for the defense training. Now, virtual reality also goes into virtual tourism. On the same day, you can experience visiting Acropolis in Athens, Taj Mahal in Agra, and Hollywood in LA. This is the kind of virtual reality which promotes tourism. So we have British Museum, which is working on for their online visitors to have this experience. Interactive films can look around the scene if they can actually you can feel that there is actually there. Amsterdam's the cinema at the Amsterdam, have revolving chat. You can catch the action on. Sports gives viewers and experiences of you actually being in the game or being in the pitch. Now, crime scenes, we are until now, the juries who decides the cases were using photographs. Now they could be virtual realities which can stitch up these photographs and give you a more realistic, crime scenes. Therapy, the therapy from a stroke or a brain injury kind of a patients, VR can help facilitate this in a very safe and anxious-free environment. So if a person is being asked to walk on a treadmill, walking in with VR can be giving him a feel that he's walking on a similar path which he's traveled before. So that's going to be a safe and an anxious-free. From we have hotels in LA which facilitate this experience at a $20, and it enhances customer experience with the safe, safety of individuals. These were some of the use cases which you did see from virtual reality, which is under the URLLC. Now, position accuracy is another beautiful use case which I do have from URLLC kind of an application under the 5G. This is for high accuracy positioning. What is expected is quick, reliable, and should be made available with position accuracy is what it demands for. Thus, high reliability is required, high availability is required, low latency, and low data rate requirement. So what it promises is in an a car collision kind of a scenario. It is not only the object to be identified, but also the surrounding to be given a priority. So that's a kind of a high accuracy positioning gives into. So I have some of the use cases here. High accuracy position is needed for collision avoidance of vehicle. So it is expected that the accuracy would be measured within 1 meter with 95% of the service made available. This is going to be getting connected to a G node, be kind of a supporting for higher accuracy scenario. Now these are some of the use cases here. So good to know here. The 5G network will control the vehicles, navigation using enhanced position signaling. So what it does is today a lot of countries government end up paying a lot of money for painting these pedestrians, painting the walkways, and even spending on traffic signals. So this all can be eliminated. However, we could be eliminating. So 5G network can broadcast these informations of where the lane is, where the pedestrian is, where the dividers are on the windshield of your on your automobile, on a car. So with the positioning accuracy. So if the car is moving at a particular region, it knows that at this particular coordinate there is a signal, and what is the signal? It is to be following the rules and regulations of that signal. So I need not physically have a signal or a pedestrian or lanes painted. So that's a huge amount of savings as well. So this is achieved by a V2X kind of a communication, which is a vehicle to infrastructure kind of a communication. Similarly, there is high accuracy positioning, which is V2V kind of a scenario, vehicle to vehicle kind of a scenario. So as we've seen, the zebra crossing, cross loan, all these kind of cost can be saved. And also moving into the next little window here, if you see a crossroad, we imagine there are two vehicles which are coming closer to this crossroad. These can be controlled with an accuracy of 1 meter accuracy with 100 milliseconds of latency, and uses a V2V kind of a communication, vehicle to vehicle kind of a communication. Each vehicle knows where the position is, so the two vehicles safely can pass the intersection at a time difference of 1 second. That's a huge amount of advancement with is only 17 meters of gap after one passes on, and the vehicle is expected to move with 60 kilometers of hour. So that's a huge amount of solution in which the traffic signal, the traffic jams can be overcome. So what eventually it also helps us is, if you see the point number two, reaching a destination in the future would not be difficult or take a long time on the road. Say in the middle of a city, I would be able to ride what I'm doing in a highway. So 200 kilometers speed can be achieved even in a city if this is calculated on an accuracy with a 1 second with 17 meters of gap. So this could turn out to be a solution towards the traffic jam, as we discussed. So this is the picture how the heat map, which shows how the vehicles are controlled. So I have a little video. So see, since I have a little more time, let me play this video for you. This is one of the video which shows a vehicle to infrastructure kind of a communication in the coming technologies. This is with the 4G technology. It is going to go much more than this one. So welcome back. So that's the power of technology, which is going to come up, and much more than that is what we would be seeing with 5G. So what you see here on the screen here is some of the test cases. Way back in 14th, close to 14 May 2018. This was the 5G trial, which was achieved to 2 gigahertz of trials, which was achieved. And similarly, I also have from a Qualcomm kind of a scenario where the wireline kind of an experience was achieved. That is, 1 millisecond with a latency, 1 milliseconds of latency with a throughput of 10 gigahertz, 10 Gbps in fact. So that's it from my side, and thank you very much. So let me see what questions I have from the chat box. Okay, if you have any questions, you can type into the box. I do not find any as at present. So by the time people come out with the questions, there were two videos which I did skip. So since I have another 10 minutes to go, I can take you to one of the videos, hopefully. Maximum. Maximum. Yeah. So welcome back here, and thank you very much for joining in and taking your time for this the last 2 hours. And if you still have further queries, you can mail us. Happy to respond to any of these queries. And thank you very much, and have a great day. Thank you. Bye bye.